In this lesson, we are going to look at the principle of operation and construction of an airspeed indicator, or ASI. We will also consider the matter of calibration, and the relationship between indicated airspeed, calibrated airspeed, equivalent airspeed, and true airspeed. The ASI is an air pressure sensing instrument, so let us begin by first considering the air pressure the ASI is required to sense. An aircraft which is stationary on the ground in still air conditions will be subject only to ambient atmospheric pressure, or static pressure, which we can see here represented by the red arrows. In forward motion, the aircraft will be subject to an additional or dynamic pressure, represented here by the blue arrows. The total pressure the aircraft will be subjected to will therefore be the static pressure plus the dynamic pressure. This is known as total pressure or pitot pressure. The dynamic pressure experienced by the aircraft will vary with the speed of the aircraft through the air, and mathematically this relationship is expressed in the formula dynamic pressure equals a half rho v squared, where v is the true airspeed and rho is the density of the air. So, if dynamic pressure can be isolated from the total or pitot pressure, it can be used to indicate airspeed. The function of the airspeed indicator, therefore, is to isolate the dynamic pressure from the pitot pressure and to display the dynamic pressure calibrated as airspeed. Logically, the airspeed displayed on the airspeed indicator is known as the indicated airspeed, or IAS. The airspeed indicator, or ASI, can be thought of as an airtight box, or instrument case, into which the static air pressure is fed. Diagrammatically, the instrument is shown here, and on our diagram we will call the static pressure S. Inside the instrument case is a thin-walled metal capsule, which is capable of expansion and contraction. Pitot pressure is fed into this capsule, and we can see this capsule represented here in blue. We will call the pitot pressure dy plus S. The pressure inside the metal capsule will therefore consist of static pressure plus dynamic pressure, whereas the pressure inside the instrument case will consist only of static pressure. As the static pressures inside both the instrument case and the metal capsule are equal, any expansion or contraction of the metal capsule will be due to the presence of dynamic pressure only, as the static pressures cancel each other out. Expansion or contraction of the metal capsule will therefore be related to the changes in the dynamic pressure produced by changes in airspeed. Click on Increase Airspeed or Decrease Airspeed to see the principle in operation. Let us look now at the matter of calibrating the ASI. Although we can say that dynamic pressure is proportional to speed, the formula dynamic pressure equals a half rho v squared shows us that dynamic pressure is also proportional to the air density. The density of air changes with temperature and pressure, and will therefore vary with altitude. If we think about it, if the air is less dense, the airspeed required to produce the same dynamic pressure will have to be greater. Remember, the ASI is actually sensing dynamic pressure, which has been represented on the dial of the ASI as airspeed. Therefore, the ASI can only indicate the true airspeed, or TAS, at the density for which the instrument is calibrated. No allowance can be made in the calibration for the change in air density, which occurs with change in altitude. In practice, the ASI is calibrated to read the true airspeed only for the air density of 1,225 grams per cubic meter. This is the air density on which the International Standard Atmosphere, or ISA, is based. ISA also assumes a mean sea level air pressure of 1013.25 millibars or hectopascals and a temperature of plus 15 degrees Celsius. Use the mouse to move the aircraft, and you will see that as the altitude of the aircraft increases, the indicated airspeed remains the same, but the true airspeed increases. We have to make corrections, therefore, to determine the true airspeed from the indicated airspeed. We will look at these corrections and identify the errors which require correction, in the order in which they are usually applied to the indicated airspeed, or IAS, to enable the true airspeed, or TAS, to be calculated. The first error to consider is instrument error. Manufacturing imperfections, friction and play in the moving parts of an instrument affect the accuracy of the instrument. Under laboratory conditions, individual instruments can be checked by reference to a datum instrument, and a correction card can be produced for the speed range of the instrument. The second error in order of correction is position error, which is sometimes known as pressure error. Position error occurs as a result of suction and turbulent airflow in the vicinity of the pitot-static heads, which feed the air pressure instruments. The corrections applied to the indicated airspeed for instrument and position error give us calibrated airspeed. A correction card on the aircraft will combine the corrections for both instrument error and position error into a single correction table to give us calibrated airspeed, or CAS. Note that calibrated airspeed is sometimes referred to as rectified airspeed, or RAS. To summarize so far then, the indicated airspeed, plus or minus the instrument and position error corrections, gives us the calibrated airspeed, or CAS. In practice, the next error we usually have to correct for is density error. We can use the CRP5 or similar navigation computer for this correction, and how to use the computer is covered in the specific lesson on the navigation computer. Earlier in the lesson, we saw that the ASI is actually reading dynamic pressure, displayed as airspeed, and we saw that the indicated airspeed will only be the same as the true airspeed at the air density of 1,225 grams per cubic meter. At air densities other than this density, the ASI will not indicate the true airspeed, or TAS. This is known as the density error, and density error can cause the ASI to underread the TAS by a considerable amount as altitude is gained. Note, however, that if the calculated TAS is greater than 300 knots, then a correction for compressibility must first be applied to the CAS. So, if the calculation for TAS results in a TAS of more than 300 knots, the remaining correction to consider is known as compressibility error, and we have to go back to the CAS to apply this correction. Air is compressible, and at high speeds the air compresses when brought to rest in a pitot pressure system. Consequently, the pressure sensed will be artificially high, which will cause the ASI to overread. Near the speed of sound, the error can be more than 20 knots. The correction for compressibility error gives us equivalent airspeed, or EAS. The equivalent airspeed is the most accurate measurement of dynamic pressure, as it has been corrected for instrument, pressure, and compressibility error. However, in practice, it is rarely necessary to calculate the EAS in order to determine the TAS. This concludes the lesson.